In this lecture, we are going to discuss yet another hypothesis called the random walk hypothesis, which is more mathematical and more in line with the topic of this section, which is time series analysis. In fact, we'll see very shortly that the random walk is just a special case of the ARIMA model, which we will be studying in this section. The random walk hypothesis is similar, but not the same, as the efficient market hypothesis. Put simply, it says that stock prices follow a random walk. Of course, you may not know what a random walk is yet, but that's what this lecture is about. When we did our price simulation earlier, we actually assumed that stock prices follow a random walk, although you may not have known this at the time. Because of the nature of random walks, if stock prices do in fact follow a random walk, then they are unpredictable. The rest of this lecture will show you how. But first, let's discuss some of the history behind the random walk hypothesis. Firstly, the mathematical concept of random walks has existed for a long time. As you'll see, it's just a Markov process, and so it's something you would normally learn in probability class. The random walk hypothesis is specific to finance and stock prices in particular. It was popularized in the 70s when a book called A Random Walk Down Wall Street was released. In fact, this was the book that also popularized the efficient market hypothesis. Note that both the random walk hypothesis and the efficient market hypothesis lead to the same conclusion, which is that you can't beat the market. Now, of course, there are people who don't believe in the random walk hypothesis, and so another book has come out called A Non-Random Walk Down Wall Street. Interestingly, this book came out almost 30 years later after A Random Walk Down Wall Street, so it's not as if the random walk hypothesis and the efficient market hypothesis are ideas which are easily debunked. Later in this section, we're actually going to fit models to stock prices, and we'll find that sometimes the best fitting model is in fact a random walk. So what is a random walk? Well, probably the simplest random walk works like this. Start at any price. Then, in order to generate the next price, simply pick either +1 or -1 with equal probability. So P1 is equal to P0 plus E1, where E1 can be either -1 or +1. Then generate P2 from P1 in the same way, by picking either +1 or -1 with equal probability, and then adding it to P1. Then we find P3, and then we find P4, and so on. So this is a random walk. Basically, you can imagine yourself walking on the sidewalk in one dimension. At every step, you either decide to take one step to the left or one step to the right based on the result of a coin flip. Your walk is then a random walk. Notice one important property of the random walk. It's impossible to predict the next value. You only have a 50% chance of getting it right. In other words, your ability to predict the result of your walk is the same as your ability to predict the result of a series of coin flips. Now, we know that changes in stock price aren't just -1 and +1, but can be real valued. In fact, we spent a lot of time in the previous section of this course trying to figure out what is the distribution that stock returns follow. Let's assume for now that the noise term E is Gaussian. What would our algorithm be for generating stock prices? Again, we start at P0 equal to some arbitrary value. To find the next price, we first sample E from our Gaussian. Then we add P0 plus E1 to find P1, the next price. We do the same thing to generate P2 and P3 and so forth. This should sound familiar because it's exactly what we did in our price simulation exercise from the previous section. In fact, that was exactly a random walk. Notice again how we can't predict P1 from P0, or equivalently, we can't predict P1 minus P0, which is just E1, which is Gaussian noise. We can only predict E1 insofar as we know its expected value. Here's something interesting we can do that helps us understand why working with log prices is valuable. The general formula for a random walk with a drift is as follows. Mu is called the drift term, and it's considered to be constant. If you're thinking of a time series, this would control the trend of the time series. E of t is a Gaussian with mean 0 and some variance sigma squared. In this case, p at time t and p at time t minus 1 are the log prices at time t and time t minus 1, respectively. Note that if I take p at time t minus 1 to the left-hand side, I get p at time t minus p at time t minus 1, which is the log return. If we were working with non-logged returns, this wouldn't be as convenient, since we would need p of t minus 1 in the denominator to represent the return. What this says is that the log return is just the thing on the right-hand side, which is just a Gaussian with mean mu and variance sigma squared. So the random walk model goes hand in hand with log prices and log returns. In fact, this model is the basis for the Black-Scholes formula, which earned the Nobel Prize in Economics. Now, the big question is, of course, is the random walk hypothesis correct? Well, let's recognize that there are some hidden assumptions in the random walk model. First is that the log returns are IID, independent and identically distributed. We have seen that this may not be true because we have observed volatility clustering. If the volatility changes over time, then by definition, it's not identically distributed. Furthermore, if the volatility in one period has some relationship to nearby periods, that is, high volatility is clustered with other high volatility, then it's also not independent. At the same time, the random walk model is convenient and easy to work with. We will find that when we fit ARIMA models to stock prices, sometimes the best fitting model will be a random walk. So it wouldn't be wrong to say that sometimes, for certain periods of time, stock prices do look like they follow a random walk. As with the efficient market hypothesis, it's possible to use statistical tests to determine whether or not stock prices follow a random walk. Now, since this is a section on time series, we're going to do some time series analysis on random walks. Let's recognize that a random walk is just a specific instance of a Markov chain. If you've ever taken any of my courses on NLP or reinforcement learning, you should be familiar with this concept. The basic idea is this. Consider the sentence, "The quick brown fox jumps over the lazy dog." If I gave you the sequence, "The quick brown fox jumps over the lazy," how can you predict the next word of this sentence? Well, one solution is to build a probability distribution. So you have the probability of the word at time t given the word at time t minus 1, given the word at time t minus 2, and so on. We call such a model a language model. Well, to get to the point, the Markov assumption says this. It says that instead of the word at time t depending on all previous words, it only depends on the most immediate preceding word. That is, p of word at time t, given word at time t minus 1, word at time t minus 2, and so on, is equal to p of word at time t, given word at time t minus 1. Now, you might think, okay, that's fine, but let's make this a little less abstract. Suppose I give you the word lazy, and I ask you to predict the next word in my sentence. Of course, there are many possibilities. It could be lazy dog, but you'd probably be cheating because that's the sentence I gave you earlier. It might be lazy programmer, who is the author of this course, but again, you're going to use exogenous data to make your prediction. How about lazy student? In fact, it's quite difficult to know with any certainty exactly what the next word will be, given only a single word. Consider the word the. The next word could be practically anything. So the lesson here is that the Markov assumption is an extremely strong modeling assumption. At the same time, it's quite useful. So let's assume we have a Gaussian random walk. This is x of t equals to x of t minus 1 plus e of t, where e of t is Gaussian distributed with mean 0 and variance sigma squared. In this case, we can see that x of t is completely determined by a Gaussian distribution centered at x of t minus 1 with variance sigma squared. That is, it does not depend on any previous values in the series, not x at t minus 2, not x at t minus 3, and so on. Therefore, the Gaussian random walk forms a Markov chain. So if stock prices follow a Gaussian random walk, then the next obvious question is, how do we forecast? Remember that because the next step is essentially random, the best we can do is find the expected value. Well, the expected value of a Gaussian with mean x of t minus 1 is just the mean, x of t minus 1. So what does this say? It's saying that if your stock price follows a random walk, then your best guess for the next stock price in the series is just the previous value. We cannot do any better than this. Notice that this justifies our method of filling in missing data, which is to copy the previous stock price forward in time. Now, as you know, often when we make estimates in statistics, we also want to quantify how confident we are in those estimates. Let's suppose we start at x of t and we want to forecast tau steps into the future to find x of t plus tau. We already know the expected value of x of t plus tau. It's just x of t, the same value we started with. But what is its variance? Well, we can use our price simulation formula. We know that x of t plus 1 is equal to x of t plus e of t plus 1. Based on that, we also know that x of t plus 2 is equal to x of t plus 1 plus e of t plus 2. We just added 1 to all the time indices. However, we can substitute x of t plus 1, and then we would get x of t plus e of t plus 1 plus e of t plus 2. And then we keep following this pattern until we get to x of t plus tau. So x of t plus tau is equal to x of t plus e of t plus 1 plus e of t plus 2, all the way up to e of t plus tau. Now luckily, we did something exactly like this in the previous section. If all the e's are Gaussian with mean 0 and variance sigma squared, then their sum has mean 0 and variance tau times sigma squared. Therefore, we can say that the variance in our estimate increases linearly with tau. More commonly, we work with the standard deviation, so we can say that the standard deviation of our forecast increases with the square root of the number of forecasting steps. Let's consider a well-known theorem from statistics, the central limit theorem. We know that our forecast at time t plus tau is the last known price, x of t, plus the sum of a bunch of noise terms. Recall that the central limit theorem says that this sum tends to a Gaussian distribution. And so even if your returns do not necessarily follow a Gaussian distribution in the short term, what happens in the long term? Well, in the long term, you're just adding up a bunch of random variables, and due to the central limit theorem, their distribution approaches a Gaussian. I want to end this lecture with a tale about a famous experiment run by the Wall Street Journal in 1988. In this experiment, called the Dart Throwing Investment Contest, professional stock traders from the New York Stock Exchange competed against dummy investors who simply threw darts on a board to choose stocks randomly. Now granted, one might argue that throwing darts is not actually random, and there may have been better ways to make random choices. In any case, they found that professional investors beat the dummy investors 61 out of 100 times, and the dummy investors won only 39 out of 100 times. So you might think, it's better to go with a professional investor rather than just picking stocks randomly. However, the professional investors only beat the market 51 out of 100 times. This is why it's often advised not to use active investing, although your bank will tell you otherwise. Just don't forget your bank is there to sell you things, not to give you good advice. If you buy into an actively managed fund, first of all, you may only have a 50% chance of beating the market, and on average, you will match the market. However, the fees for actively managed funds are much higher than passively managed funds. Therefore, if you invest in the market itself, your fees will be much lower, and you will have the same expected return anyway.